Hello everyone, welcome to this lecture series on thermodynamics. Today we will discuss Kelvin scale of temperature or thermodynamic scale of temperature. We know that temperature is a measure of degree of hotness or coldness of a body. Any device which is used to measure the temperature is known as a thermometer. We have already seen that all the thermometers which we use to measure the temperature, they depend on the properties of substances like expansion of mercury, increase of volume or pressure of a gas, variation of thermo-EMF, etc. Hence, the temperature measured by these thermometers are arbitrary. That means the temperature measured by one thermometer do not coincide with that of the another thermometer. Hence, there is need for non-arbitrary scale of temperature which does not depend upon any property of the substance. Hence, such a scale is known as absolute scale of temperature. So, for the first time in the year 1848, Lord Kelvin designed a temperature scale which is independent of the nature of the working substance and depends only on the temperature of source and sink. Hence, this scale of temperature is named after his name as Kelvin scale of temperature, or commonly known as thermodynamic scale of temperature. This Kelvin scale of temperature is based on the principle of Carnot's principle, that is, the Carnot engine efficiency does not depend upon the working fluid. It depends only on the temperature of reservoirs between which it operates. Now, let's discuss this Kelvin scale of temperature. In order to understand this Kelvin scale of temperature, let us consider the operation of three engines, 1, 2 and 3. All these are three reversible engines. Now let us assume that this engine 1 is absorbing a quantity of heat Q1 from the thermal reservoir which is at a temperature T1, does a work W1 and rejects a quantity of heat Q2 to the thermal reservoir which is at a temperature T2. So it is absorbing a quantity of heat Q1, doing a work W and rejecting a quantity of heat Q. For such a type of engine, the efficiency can be written as eta 1 is equal to ratio of work done to the quantity of heat absorbed. That is, eta 1 is equal to W1 by Q1. That is equal to 1 minus Q2 by Q1, which is nothing but a function of temperature and can be written as f of T1, T2. So, where f is a function of temperature. Or on simplifying this, we can write Q2 by Q1 is equal to 1 minus f of T1 T2. Q1 by Q2 is equal to 1 by 1 minus f of T1 T2, or Q1 by Q2 can be written as capital F of T1 T2, where f is another function of temperature. Now, similarly, let us take the case of the second engine, which is absorbing a quantity of heat Q2, doing a work W2 and rejecting a quantity of heat Q3 to the thermal reservoir at a temperature T3. Then, similar to that of the first engine, we can write Q2 by Q3 is equal to f of T2 T3, where f is another function of temperature. Similarly, let us consider the working of another reversible engine 3, which is operating between the temperatures T1 and T3. That is, this engine is absorbing a quantity of heat Q1 from the thermal reservoir T1, doing a work W3 and rejecting a quantity of heat Q3 to the thermal reservoir T3. For such an engine, we can write Q1 by Q3 is equal to f of T1 T3. So ultimately, we got the three equations, the ratio of Q1 by Q2, Q2 by Q3 and Q1 by Q3. Now let's see. Multiplying equations 1 and 2, we can write Q1 by Q2 into Q2 by Q3 is equal to f of T1 T2 into f of T2 T3. On simplifying, we will get Q1 by Q3 is equal to f of T1 T2 f of T2 T3. Now from equations 3 and 4, we can write Q1 by Q3 is nothing but f of T1 T3. So f of T1 T3 is equal to f of T1 T2 into f of T2 T3. Since T2 does, now if we observe this equation 5, we can see that on the left hand side there is no T2, but there is T2 on the right hand side. Even though there is no T2 on the left hand side, we are saying these to be equal. If this is to be true, then this function should be of the form f of T1 T2 should be of the form phi of T1 by phi of T2, and f of T2 T3 should be of the form phi of T2 by phi of T3, where phi is another function of temperature. Now let's see whether it is true or not by substituting these values in the equation. So the above equation 5 can be written as f of T1 T3 is equal to, by substituting these values, ultimately we will arrive at f of T1 T3 is equal to phi of T1 by phi of T3. So what is f of T1 T3? Phi of T1 by phi of T3. That means Q1 by Q3 will become phi of T1 by phi of T3. Hence, what we have assumed is correct. That means it is a function of phi is another function of temperature. Now equation 1 can be written as Q1 by Q2 is equal to f of T1 T2. So f of T1 T2 is nothing but phi of T1 by phi of T2. We know that T1 is always greater than T2 and Q1 is always greater than Q2. Then the function phi of T1 should always be greater than phi of T2. This implies that phi of T is a linear function of temperature. Hence, Q1 by Q2 is equal to T1 by T2. From this equation, it is very clear that the ratio of quantity of heat energies, that is the ratio of heat energy absorbed to the ratio of heat energy rejected, is equal to the ratio of temperature of the source and temperature of the sink. That is the temperature of the hot reservoir and temperature of the temperature of the cold reservoir. This is nothing but the Kelvin scale of temperature. That means it depends only on the temperature of the source and sink, but it is not depending on the nature of the working substance. So this can be taken as the absolute scale of temperature, or we can call it as the Kelvin scale of temperature. Hope you have understood Kelvin scale of temperature. Thank you.